Welcome to this college algebra video, Chapter 2, Section 1, on the topic of computations with coordinates. I'll be showing you a few of the common formulas used with coordinates and some examples of how to put those formulas into practice. So we're going to begin with just a quick review of plotting coordinates and the idea of the quadrants in the XY plane. So given these 4 points, why don't you take just a second and try to plot them yourself. All right, if you've had a chance to try that yourself, go ahead and take a look at this and I'll show you what this should look like here. Point A has coordinates 3, -4. So I'm going to go 3 to the right. First coordinate is the X coordinate, and 4 down. Second coordinate is the Y coordinate. The point 3 over and 4 down appears here. That is point A. Point B is 2 to the left. So the X coordinate is to the left and 5 units up. 1, 2, 3, 4, 5. So point B is located in the upper left. Point C has coordinates 3, 3. So that is 3 to the right and 3 up. And finally, point D has coordinates -4, -1. That is 4 to the left on the x-axis and 1 down in the y direction, and there's point D. So these quadrants that we're talking about here are the 4 sections of the plane that we can see sectioned off by the 2 coordinate axes. Point C is in the quadrant that we call quadrant 1. Use Roman numeral 1 to represent that. Point B is in quadrant 2, and we continue around in a counterclockwise fashion here. Point D is in quadrant 3, and point A is in quadrant 4. Something you'll notice is that the signs of X and Y are all the same in a particular quadrant. So in quadrant 1, we always have a positive X and a positive Y. In quadrant 2, we always have a negative X and a positive Y. In quadrant 3, both coordinates are negative. X is negative, Y is negative. And in quadrant 4, we have a positive X coordinate, but a negative Y coordinate. So that's just a quick review of the quadrants. All right. Our first idea that we want to talk about relating to coordinates is directed distance on a number line. So moving back from kind of two-dimensional thinking back to just one dimension, being able to move along a number line, not up and down, but just side to side, we're going to talk about directed distance. And when we're talking about this kind of distance, pay attention to the language that's used. We'll often talk about the distance from one coordinate to another coordinate, instead of talking about the distance between things. There's a particular order to this. So moving from one coordinate to another coordinate, the concept works like this. The directed distance from A to B, we find that by calculating B minus A. Now, depending on the numbers we're subtracting here, this directed distance can either come out positive or negative. Sometimes we talk about distance and we always want that distance to be positive, but for these cases, the directed distance has a sign associated with it. So for example, the directed distance from 2 to 7, you compute it by 7 minus 2 and equals 5. But the distance from 7 to 2, compute it by 2 minus 7 and you get -5. So we're referring to these distances as directed distances, and the positive and negative are referring to the direction that you move. To go from 2 to 7 on a number line, you'll move to the right. To go from 7 back to 2 on the number line, you'll move to the left. So positive and negative refer to moving to the right and to the left. That's why we call this directed distance. A second concept we're going to look a little bit at is the idea of finding a coordinate that is some fraction of the distance from a beginning to an end. So x1 is our beginning coordinate, x2 is our ending coordinate. I don't want to find the distance all the way from x1 to x2. I want to go some fraction of that distance from x1 to x2. And if this is a proper fraction, we're going to wind up somewhere between x1 and x2. The big overall idea that we're going to look at here is a start plus a change produces an end. And that should be pretty easy to understand. If we start somewhere and don't make any change, then we're not going anywhere. If we make 100% change, we're going to get all the way to the end. If we make some fraction of a change, we'll get part way to the end. So we'll be beginning at x coordinate x1. We're going to go some fraction of the directed distance from x1 to x2, and we're going to wind up at a new x value. That new x value is going to be somewhere between x1 and x2. Here's an example. And we'll continue to use this formula. That might be a good formula to write down if you're taking notes. Examples. Find the coordinate on the number line that is 3/5 of the distance from 2 to 27. So we've got a starting point 2. If we go all the way to 27, we'll be at 27. We're going to go some fraction of the way from 2 to 27. We'll wind up at some x coordinate in between 2 and 27. Well, here's the formula we were using. Recall, x1 is going to be our starting point. That's 2. x2 minus x1 is 27 minus 2. The fraction that we want to go is 3/5 of that directed distance. So filling in all the numbers with the 2, the 27 minus 2, and the 3/5, now it's time to do some calculation. 27 minus 2 is 25, and 3/5 of 25 is 15. So my starting position was 2, I have a change of 15, and I end up at coordinate 17. As a second example, find the coordinate on the number line 1/3 of the distance from 4 to -14. We're going to continue to use this formula. Now, if you find that formula a little bit hard to memorize, maybe you just want to remember the big overall thing we're doing, a start plus a change. So the start is that first coordinate, we've got 4. And the change is 1/3 of the directed distance. 1/3 of -14 minus 4. So doing some calculation here, that is 4 plus 1/3 of -18. 1/3 of -18 is -6. So 4 and -6 add to -2. That is our ending position. We start at 4, we change by this amount, -6, and we wind up at coordinate -2. And notice -2 is partway in between 4 and -14. In fact, it is exactly 1/3 of the way from 4 to -14. The next concept we want to talk about is distance in the XY plane. So not just moving side to side along a single number line or along a single axis, but this time distance between 2 points in the 2-dimensional plane. The distance formula, as you will learn it in any textbook, looks like this. D is equal to the square root of x2 minus x sub 1, that quantity squared, plus y sub 2 minus y sub 1, that quantity squared. That is quite a mouthful. That is quite the formula to try to memorize. So what I suggest, instead of trying to memorize that, is remember the concept that this comes from. And if we do, we can simplify things a little bit. I would memorize this distance formula in this way. Distance equals the square root of delta x squared, that stands for a change in x, plus delta y squared. That stands for a change in y. Now, if you don't like the Greek letter delta and notation delta x standing for a change in x, change in y, then there's even a simpler way to memorize this formula. Distance equals square root of horizontal squared plus vertical squared. This version of the formula comes from the fact that finding a distance on the coordinate plane is essentially using the Pythagorean theorem. We're trying to find this blue distance I've labeled d, and that is a diagonal distance. Of course, I could break that diagonal distance down into a horizontal component and a vertical component. Those two components are the legs of a right triangle. So d squared is equal to horizontal part squared plus vertical part squared, or d is equal to the square root of the horizontal squared plus the vertical squared. Now, this kind of distance always comes out positive. Unlike the directed distance that we talked about just a minute ago, we always get a positive answer when we use the square root or radical symbol. So simply remember that this formula is based on the Pythagorean theorems. A squared plus b squared equals c squared, where c is the distance we're trying to find, a is the horizontal component of that distance, and b is the vertical component of that distance. A second formula that you need to know relating these coordinates in the coordinate plane is how to find a midpoint. This formula is given in a textbook like this. Midpoint equals parentheses x2 plus x1 all divided by 2, comma, y2 plus y1 all divided by 2, close parentheses. Really what this is a way of finding coordinates. The first part of the formula here tells you how to find the x coordinate of the midpoint. The second part tells you how to find the y coordinate of the midpoint. Now, a simpler way to memorize this is to simply think of the midpoint as the average x value and the average y value. How do I find an average? I simply add two things and divide by 2. So if I add the x coordinates and divide by 2, I get the x coordinate of the midpoint. If I add the y coordinates and divide by 2, I get the y coordinate of the midpoint. Let's look at a few examples here. I've got those same 4 points that you plotted earlier at the very beginning of this lesson. First, I'm going to find the distance from A to B. So point A, coordinates 3, -4, point B, coordinates -2, 5. Remember, my distance formula is square root of a horizontal component squared plus a vertical component squared. To find that horizontal component, I want to look at these x coordinates for A and B. The coordinate 3 and the coordinate -2 are 5 apart. So I'm going to put a 5 in this first parentheses. The y coordinates, -4 and 5, are 9 apart. So I'm going to put a 9 in the second parentheses. 5 squared plus 9 squared. That's the same as square root of 25 plus 81. Now, important thing, don't try to take the square root now. Don't try to square root each of these separately. We're not allowed to do that with addition. We need to combine these. We'll get 106. So our answer is the square root of 106. That's the distance from A to B. Next, I'm going to try to find the midpoint of the segment going from A to B. Midpoint of segment AB. And remember, the formula there is I need to average. First, I'm going to average the x coordinates. So 3 plus -2 divided by 2. Next, I'm going to average the y coordinates. So -4 plus 5, all divided by 2. Simplified, that is 1/2, comma, 1/2. Now, just a quick word about notation here. The distance AB, when I write AB next to each other, that stands for the distance from A to B. If I put a line over the letters A, B, that stands for the segment AB. As a second example, let's find the distance from point B to point D. So again, let's find that horizontal component. Between -2 and -4, I only have a distance of 2. Those are only 2 apart. Don't try to add them and make it 6. Those coordinates are only 2 apart. So in the horizontal parentheses, I'm going to put a 2. Vertically, we have the coordinates 5 and -1. Those are 6 apart. So I'm going to put a 6 in the vertical parentheses. Now we'll square both of those and add them up. Square root of 4 plus 36 is the same as square root of 40. Simplified, the square root of 40 looks like 2 root 10. Now let's find the midpoint for segment BD. Remember, for midpoint, we're going to find the average. I want to average the two x values, -2 plus -4 divided by 2, and average the two y values, 5 plus -1 divided by 2. That works out to -6 over 2 and +4 over 2, or in reduced form, -3, 2. So -3, 2 is the point exactly in the middle between B and D. The next thing we're going to do is we're going to see sort of a sophisticated application of this whole idea of distance. We're going to be asking ourselves, are 3 points collinear? That is, do they all line up in the same line? So just given any 3 random points, they may not line up in a straight line. If they don't line up in a straight line, then they must form some kind of a triangle. So we can actually break down all the possibilities as follows. When testing whether 3 points are collinear, or if they form different types of triangles, first we need to find the distances between all the points. So we'll use that distance formula to find all 3 distances. After that, I'm going to name them from smallest to largest as A, B, and C. And from here on out, I'll refer to that smallest as A, the middle number as B, and the largest as C. Just by looking at how A, B, and C relate, we can actually answer the questions of, are the points collinear? And if not, what type of triangle do they form? Here is a visual representation of those 3 distances, A, B, and C, a short length, a medium length, and a longer length. Notice that when the short length and the medium length together are more than the largest length C, that is A plus B does not equal C, there's no way for these points to line up in a straight line. They will form a triangle. However, if A plus B is exactly the same length as C, the only way for that to happen is if all 3 points do line up in a straight line. So when A plus B is equal to C, we know that the 3 points are collinear. If A plus B does not equal C, then the points are not collinear and we're in some situation involving a triangle. So back to the notes. Our first thing, once we've got our 3 distances, we're going to test to see whether the 3 are related in this way. If the 2 smaller lengths add up to the 3rd length. If they do, our conclusion is that these points are collinear. If they don't, we're going to go through a process not just to say that they form a triangle, but we're actually going to determine what kind of triangle they form. So if they are not collinear, we're going to run a few more tests here. So the first thing to determine would be if A, B, and C are all different lengths, then we have a scalene triangle. If 2 lengths are the same, but not the same as the 3rd length, then we've got an isosceles triangle. If all 3 lengths are the same, we have an equilateral triangle. Those are the three basic categories of triangles when we're considering sides. However, on the scalene and isosceles triangle, we're also going to try to determine one more thing. Some scalene triangles and isosceles triangles also turn out to be right triangles. And so we'll test one more thing here. We'll try to find out if a squared plus b squared equals c squared. If that is true, then we have a right triangle. We don't even need to test that for equilateral triangles. Equilateral triangles are always also equiangular, meaning they all three angles are 60 degrees. So in the case of scalene and isosceles, we'll also try to see whether we have a right triangle. If we see an equilateral triangle, there's no need to even perform this last test. So let's look at some examples. We're going to determine if these points are collinear, and if not, we'll determine what particular kind of triangle they form. So to get started on this problem, I'm going to assign some names to these points. That'll just help me keep track of what distances I've found and which ones I haven't. So I'm going to call that point P, this one point Q, this one point R. And as I find my distances, I will label them accordingly. So first distance I'm going to look at is PQ. The horizontal change for PQ is 10. So I take 10 squared. The vertical change for PQ is 2. So I add 2 squared. 10 squared plus 2 squared is 104. This is the square root of 104. There's no need to simplify this at this point. I may be able to write that square root in a simpler way, but for our purposes, it's okay to leave these square roots unsimplified. Next distance, let's find QR. The horizontal distance for QR is 6. From 9 to 3 is 6, so that's 6 squared plus vertical distance of 4. 6 squared plus 4 squared is equal to 52. So this is the square root of 52. Let's look finally at the distance from R back to P. Distance of RP, the horizontal distance from -1 to 3, that's a distance of 4. All right, 4 squared. The vertical distance from 2 to 8, that is 6. 4 squared plus 6 squared, oh, that's the same as 6 squared plus 4 squared. I think, again, I have 52 under a square root. All right, so we've got our three distances. I've got these two are smaller than the last, so I can name these A and B, and I'll name square root of 104 as C. Let's test to see whether A plus B is equal to C. All right, that is square root of 52 plus square root of 52, the same as square root of 104. Well, let's get a calculator and find out. Square root of 52 plus, oops, sorry, get out of that square root, plus square root of 52. That's about 14.42. The square root of 104 is just barely more than 10. So these are not equal to each other. So the answer is no, not equal. So these points are not collinear. Points are not collinear. Now, once we know that the points are not collinear, then we want to explore this a little bit further and decide what kind of triangle we've got. Well, I see two sides that are the same, one that's different. So I see that this is an isosceles triangle. Since two sides are the same. But in addition to that, I want to find out if this is a right triangle. And to test whether it's a right triangle, we're going to test whether a squared plus b squared is equal to c squared. If I take a 52 square root and square it, plus another square root of 52 squared, does it equal square root of 104 squared? Well, since squaring can cancel out square roots, this is really like asking, does 52 plus 52 equal 104? Well, of course it does. The answer on that is yes. So not only is this an isosceles triangle, it is also a right triangle. So we determined that the points are not collinear, but they do form an isosceles right triangle. Let's see another example. So I've got a new set of points here, -2, 7, 2, 1, and 4, -2. I want to find out if these points are collinear, and if not, do they form some particular kind of triangle? So once again, I'm going to name these points so it makes more convenient to refer to them as I'm finding distances. I'll call them P, Q, and R again. You can choose whatever letters you prefer. But distance PQ, that is horizontal distance of 4, a vertical distance of 6. Well, we did a lot of those. 4 squared plus 6 squared. That is square root of 52. Next, let's find the distance QR. The horizontal distance is 2 squared. The vertical distance is 3. 2 squared plus 3 squared, that equals 13. So this is the square root of 13. The last distance, RP, or P back to R, or R back to P, the distance between these outer 2 points is a horizontal distance of 6 and a vertical distance of 9. 6 squared plus 9 squared is equal to 117. All right, remember, once I've got my 3 distances, I'm going to label these so that the smallest is A, the next biggest is B, and the largest is C. We're going to test to see whether A plus B is equal to C. That is square root of 13 plus square root of 52 the same as square root of 117? Well, let's check that on a calculator. Square root of 13 plus the square root of 52 is about 10.81. The square root of 117 is also about 10.81. In fact, these numbers are identical. So our answer this time was yes, these distances do add up. A plus B does equal C. So our conclusion is going to be that these points are collinear. So yes, they are collinear. Since they are collinear, they do not form a triangle. We don't have to do any of the further tests. For our last example, we're going to find the coordinates of a point that is 2/5 of the distance from -2, 8 to 833. Now, based on the previous problems that we've just been doing, you might think that the first step would be to find the distance from -2, 8 to 833. It's right there in the problem, but we don't really need to use that distance formula, that square root of horizontal squared plus vertical squared. In fact, we can find this point without ever knowing what the actual distance between these 2 points is. So let me show you how. We're going to go back to that first formula that we learned here about the distance on a number line. So for instance, we used the formula x1 plus a over b times x2 minus x1, that tells us how to find a point on a number line that is some fraction of the distance from x1 to x2. If we use that same formula only for these x values, -2 and 8, we'll actually find the x-coordinate of the point we're after. So let's work this out. 8 minus a -2 is the same as 8 plus 2, so that's 10. 2/5 of 10 is 4, and -2 plus 4 is 2. So the x-coordinate of this point that I'm after is actually 2. Now to find the y-coordinate, we're just going to use the same type of formula, this time using our y values. So we found the point that's 2/5 of the way horizontally. Now let's find the point that is 2/5 of the way vertically between these 2 points. So I'll use a similar formula, just replacing x with y. And we'll find using a y1 of 8 and a y2 of 33, and this same fraction 2/5. 2/5 times 33 minus 8, well, 33 minus 8 is 25. 2/5 of 25 is 10. 8 plus 10 is 18. And so the y-coordinate of the point we're after is 18. The coordinates of that point are 2, 18. So we never actually had to find the distance using that two-dimensional distance formula at all. We could simply treat the x's as though we're independent and the y's as though they were independent. I hope this recording has helped you understand some of the concepts in Chapter 2, Section 1 of our college algebra course. Now it's time for you to try some problems. The assignment is available online at WebAssign, and please attempt the assignment and send me a message if you have any questions. Thank you.